talk about chapter 6. We're going to start out talking about Newton's laws of motion. Now, I like to give a little bit of history behind how things came to be. So let's talk about Isaac Newton first. Isaac Newton was in England in the 1600s, and he was, even from a young age, he was very brilliant. When he was in his prep school, he was outstanding in mathematics. He went into the university there. Universities already existed in the 1600s. And by the time he was about 18 years old, 16 to 18 years old, he was already doing math more advanced than the professor there. And the professor said, let's just hire him as a professor. So he was hired as a professor at a university, very young age, because of his skills and his ability to do mathematics. Now, the best thing that happened to Newton, this is how weird things happened, was that when he was about 22 years old, the Black Plague came through Europe, and specifically through England. And so the way you survive is the same way we tried to survive a pandemic here, is you spread everybody out. You isolate people. The people that die in the plague are the ones in the city. The ones when the squalor, where it's dirty, there's rats, they can't get away from all the disease. But all the rich people, anybody that had any money or anywhere to go, would all scatter to the country, go to their country estates, and then they would block it off and not let anybody in or out until they just let the plague run its course. And within a year or so, the plague would go away and everybody would come back to the normal behavior. But during this time, Newton went and lived at his grandparents' place, which was out in the country. And he didn't have any responsibility. He wasn't teaching classes. He didn't have anything else to do. So that was when he spent all his time, almost all his time, studying and learning new things. This was, that year when Newton was 22, was the most productive year in physics ever. During that time, he came up with his laws of motions. He figured out the law of universal gravitation. He invented calculus. He measured the speed of sound. He even investigated light. So, I mean, it was a really good year for physics. Now, the interesting thing about him is he wasn't going to publish any of this. He had done all this work, but he wasn't going to publish it. And it took a guy named Edmund Halley, who was working at the Greenwich Observatory in London, who was looking at comets, and he was looking at historical records, and he realized that every 76 years there was a bright comet. And he wondered if it was the same comet coming back every 76 years. Up until then, they thought it was a different comet all the time. And so he went to the Royal Society, which was a group of scientists at the time that would meet in London. And he said, hey, could this be the case? And they said, go talk to Newton. He's worked on this. So he went and talked to Newton. Newton said, yeah, under my law of universal gravitation, objects will orbit in elliptical paths, and it could be the same comet coming all the time. And Halley said, well, why don't you publish this so that the world knows that you figured this out? And Newton was hesitant at first. He says, I don't know, they're all below me, they don't understand me. He was very arrogant. But Halley convinced him that if he did this, it would make him famous. And he could then use that fame to get things he wanted, like he always wanted to be a knight. Which is very important, because once you were a knight, you became Sir Isaac Newton, then you had certain rights. You had rights to vote, you had right to own land, you could pass it on to your offspring. He didn't have any offspring. He never married. He never had children. He never seemed to have a girlfriend. Never even had a boyfriend, so it wasn't that he was gay. He was just pretty much didn't even care. It was kind of the way he was. So he was an interesting guy, Newton was. In fact, later on in his life, he was hired by the mint to stop counterfeiters. Because that was right when they first started using paper money, and counterfeiters would just copy it. You know, people with very detailed would copy it. And so he would design the bills to make it tougher to copy. He would do elaborate things. He would even misspell words deliberately so that when they copied it, they would copy it the right way because they thought that the one that they had was the counterfeit. He would realize that wasn't the counterfeit. And then when they catch a counterfeiter, he would go to their trials and he would sit in the balcony and snicker and make rude comments the whole time. So Newton was an interesting character all the way around. But his laws of motion pretty much define this whole class that you're taking down right now. And our laws of mechanics were completely defined by Newton 400 years ago. Okay? It wasn't until we started getting into bizarre realms that Newton's laws don't work, meaning you get close to the speed of light or in a highly accelerated reference frame, then you have to go to Einstein's theory of relativity. But for everything else, Newton's laws work great. So, these are Newton's laws. Now his first law did not come up by him. His first law was inertia. But he realized inertia was correct, but he didn't come up with this idea. This idea was developed by Galileo. Now the interesting thing about Galileo over in Italy is Galileo died the same year that Newton was born, so that keeps it kind of in reference. But Galileo was the first one to realize that inertia is a property that objects have. That the object will maintain its motion, whatever its state of motion is, unless acted upon by something else. Okay? And Newton realized that's the first law. An object wants to maintain its state of motion. If you want to change that motion, you have to do something to it. Okay? And so inertia just says that an object wants to maintain its state of motion. Or what that really says is that it has a constant velocity. Now that velocity could be 0, or it could be a number, but constant velocity means it's going in a straight line at the same speed all the time. Right? Because velocity is speed and direction. Now to change that velocity, or to change the state of inertia of the object, you have to apply a force. And Newton's law says that the force that you apply is equal to the mass of the object times the acceleration. So, the more massive the object, the bigger the force to make it accelerate. And vice versa. And so, it's very simple here, but we've got to be careful. This says the force, but what we really want to say over here is not force. We want to say that the net force. Because as we saw in chapter 5, most objects have more than one force acting on them at any given time. It's just a lot of the forces cancel out. Like gravity and the normal force keeps us from going through the floor. But they're always working. They're still there. They're just canceling out. So it's the net force that equals your mass times your acceleration. And 3, we learn this as equal and opposite. Which means, and we talked about this before, if you have a force on one object from another object, there's an equal and opposite force on the other object. Two things contact, there's always an equal and opposite force. Now the key to the third one, we're going to talk about this more in chapter 7, is that there has to be an equal and opposite force and it has to be on the other object. Where people get confused is they try to look at it on the same object. It's on a different object. Alright, so those are Newton's laws of motion. So how are we going to use those to solve problems? Alright, so first of all we got to define a couple of things here. So I have to check my recording here. Okay, let's look at how we're going to handle friction forces. Remember we talked about a friction force, we write it as a lowercase. F of k would be kinetic friction, which is still force. But we're going to do this and we're always going to replace it with something called the coefficient of friction. In this case, it's the coefficient of kinetic friction. And what is that? Well, that is a value. It's just a number, okay? It's a number usually less than 1. It doesn't have to be less than 1. It can be bigger than 1 if it's something that's very sticky. But it's a value and it depends on what the materials are made of. As you know, some materials slide better on some things than others. Some things you can't hardly even move. Sometimes it slides real easy. Like ice has a very low coefficient of kinetic friction. Where on pavement or something like that, you have a much higher coefficient of friction. And we also have static friction. The difference is, it's the mu sub S, or the coefficient of static friction times the normal force. Notice it's always times the normal force. And that's how we're going to handle frictional forces, is to replace them with this. So, remember we had 3 steps. This was in chapter 5, I'm going to go over here. First step, so solving all problems, first step is you make a free body diagram. Then you take components. You take components of any force that's not already on an axis. You make sure the axis is in the direction of motion. And then 3, you solve for F net x, F net y. But now the difference is this. If the object is not moving, if it's stationary or it's at constant velocity, then we're in the inertial state. Right? It's not accelerating. So we're in inertial state. That means that these have to be equal to 0 if it's at a constant velocity. If it's accelerating, then we have to replace the net value with ma. If it's accelerating by Newton's second law, we have to replace it with ma. And it depends on which way it's accelerating. If it's accelerating in the x direction, you're going to have m times a in the x. If it's accelerating y, you'd have m times a sub y. In our case, we always want to rotate the axis so that the object is only moving in one dimension. So it's either going to be x or y. You're never going to have it in both directions. Not until we get to chapter 8. So right now, I always keep it in just one of these will be ma, one of them will be 0. So it depends on the situation. So let's do some problems.